Hi everybody, this is Joe again, and I'm teaching grade 12 physics with AEC in Winnipeg on Main Street. And this will be number 3, I believe, of our series on impulse and momentum. By the time I'm done, I should have about 8, 9, or 10. I'm not sure how this is going to work out. So I hope everybody's hanging in there and doing fine. Please stay in touch through the email and let me know how things are going, okay, for you both personally and as we go through this course together. There's lots of unknowns in this life, and we're in this together, and so stay in touch because that's why we need to stay in touch, because every day things will change. All right, so back to this example that I promised you the other day. It's about a person jumping out of a plane and pulling a parachute cord. And remember, last time we were talking about um, momentum being conserved, but we were in a horizontal direction. This time we're just going to change things up a little bit and turn it into a vertical direction, so thus the airplane. And I'll just let you take a second to write this down. I'm going to try and do this for you, okay? A parachutist jumps out of a plane. She pulls the cord and begins slowing down until the chute is fully open 9.5 seconds later. Okay, I'll give you, you can pause the recording and get that written down. Okay, and I'm going to just go through this. Okay, so let me move my easel here. And we're going to talk about this thing. This question has so many different ways of looking at it. We can only scratch the surface, really. So what have I given you? Well, I've only given you so far that the time is 9.5 seconds. What's happening in that 9.5 seconds? Well, the girl's falling out of the plane and she pulls the cord. I'm told it's a rip cord. And at that time, when she pulls the cord, her chute begins to open, and 9.5 seconds later, the chute is fully open and she is traveling toward the earth at a constant velocity or speed at that time, 9.5 seconds. Okay, I'll give you some more information about her. She has a mass of 82 kilograms. Let's see, at time equals 0. So at the time she pulls the rip cord, her speed will be 28 meters per second going down, obviously. 9.5 seconds later, so at t is equal to 9.5, her speed is 3.0 meters per second. So in that time frame, she went from 28 meters per second to 3 meters per second. And here's the question. Determine the average force exerted by the parachute using two different methods here. The first one is the impulse momentum theorem. Okay, that's the one we've been talking about. That's the formulas where we have J is equal to F delta T, P initial total is equal to P final total, all of those ones. So the impulse momentum theorem and kinematics. Oops, and kinematics is right down there. Okay, so that's what we're going to do with this question. And all right, so currently in production, that's what we're doing right now. I'm going to declare that the down direction, here, put this back up again. I'm declaring that the down direction be positive. When you declare something as positive, that means the nature of your answer is going to have a meaning. So here we have V initial. The initial speed is 28 meters per second. Notice I have no negative sign. It's going down this way, 28 meters per second. The final velocity is 3.0 meters per second. And there we are with our delta t again, 9.5 seconds. And the question was, determine the average force exerted on the parachutist during this time frame. So you'll recall this formula here, J is equal to F average delta T. So what we'll do is we'll rearrange that a little bit. And we want to know force, the average force, so we're going to rearrange that to say J is equal to delta T. Now, J, you don't have it directly, do you? But we do know that J is also equal to, think about that for a second. J is the impulse, isn't it? It's the change in momentum. So because J is equal to the change in momentum, I'll just write that over here, equals change in momentum. We know that the change in momentum comes from the following formula. We can create this, mass times, now we have final minus initial. So we're going to go 3.0 meters per second. I'll put that in. Minus 28 meters per second. Now, I should have actually put the mass in there, but anyway, so this is V final. This is V initial. So let me carry on. We've got 82 kilograms. I say now, as I've said in class, if you need to find out where I missed a step, or if you're inclined that way, then double space your work. Okay, what do we have here? We have 3 meters per second minus 28 meters per second. That gives us a total of negative 25 meters per second. And I'll be a good boy here and I'll put my kilograms right there. So J, or the impulse, is equal to the change in momentum, which is equal to 82 times negative 25. And that is going to be negative 2,050 kilogram meters per second. Put my little squirrely, twirly S in there. Wow, it looks like I'm going downhill. So, what does negative 2050 mean? Oh, negative in this case must mean up. The impulse is up. So, let's carry on with what I said over here. We said average force is equal to the impulse divided by the change in time. So let me just have a seat and I'll say so. F average, can I see that? Just barely. F average is equal to J over delta t is equal to negative 2050 over 9.5. And I'm going to just use red pen to make this stand out a bit, okay? Negative 2050 kilogram meters over seconds, and that's all divided by 9.5 seconds. So that's going to be seconds. And so we have the average force is equal to this value divided by that value. And we are going to have, let me just get this down here. We are going to have 2016. These units over here, kilogram meters per second, all divided by seconds, become kilogram meters per second squared. And guess what? Those units work out. Kilogram meters per second squared are basically the building blocks of what we know now as a Newton. And so the average force is, and oh, let me just put this in here, the negative sign. Negative 216 kilogram meters per second squared, and that must mean the force is upward. All right, and I just want to do one more little thing here. I asked you to do this using kinematics, and ran out of paper, so I had to invent my own paper here. So thanks to Cheryl for giving me these oversized pieces of paper from the printer. And we're going to do the same thing with kinematics this time. That's the beauty of these questions. You're not always stuck to doing things one way. So remember, we're talking about the average force, and I'm going to use the kinematics here. So let me just go for this. I'm going to say V1 is equal to 28. V2 is equal to 3. T is equal to 9.5. I'll say delta T. Okay, let me put my units in here. Be a good boy here. And what is it we wanted to know? Well, we want to know the force, but you know that force, actually I should have asked using kinematics and dynamics. So anyway, I've just done that. So let's see, what can we find out? We can't really find out anything yet, but we do know this. We can solve for the acceleration. We'll do that as an intermediate step. And you can use the formula A is equal to V2 minus V1 over T. And if you work that out, you will get 2.63 meters per second squared. All right, so I'll carry on in red. We'll go over here, and remember Newton's second law says F equals ma. Ah, yes, F equals ma. Oh, that's good. Okay, so F is equal to 82 times 2.63. And guess what you get? you get 216. And I want to just, before I end this video, I want to end asking you to think the nature of this number, 216. I just gave you the absolute value of the number. Is there something fishy going on here? Should that be a negative 216, or is 216 good enough? And I want to put this high. This is not coming out all that great. Okay, so I want you to think about that. That is going to be all for impulse and momentum in one dimension, either horizontally or vertically, okay? So I will see you in the next video. Thanks a lot. Have a great day.